Hello, everyone. Welcome to section 4.3. This section, we will be talking about logarithmic functions. So before we talk about logarithms, let's go back and talk about something we've already seen a little bit. Let's look at an exponential function again. So if we have an exponential function, and let's just say it's some generic exponential function, just a to the x. And let's look at what its graph looks like real quick. So we already kind of know what exponential function graphs look like. We kind of do this, right? Now, you might notice something about this graph. It looks one-to-one. It looks like it would pass the horizontal line test. Like, sure, this tail end on the left looks like it's getting flatter and flatter, but it never does. It's just asymptotically approaching the x-axis there as you take x to be closer and closer to negative infinity. So let's write that down. It looks one-to-one. And in fact, it is. So if the function is one-to-one, it has to have some sort of inverse. That inverse is a logarithmic function. So let's go ahead and define what a logarithmic function actually is. Let's go ahead and we're going to have some number a greater than or equal to 0. The logarithmic function with base a, which is denoted log log and then a little a underneath, is defined by so we've got log base a of some number x. It's a function. So I guess for clarity's sake, I'll put a little x here too. Sometimes people leave the parentheses off if it's really clear what's going on. I'll show you what that looks like in a second. So log base a of x is equal to y. And that y is whatever y you have to take a to and raise it to that y power to get back x. So let me say that again, because this can be confusing. So the logarithm base a of x is equal to y, where y is the power that you raise a to get back x. So the thing you should take away from this is that logs undo exponents. They ask, write this down what I just said, what power do I need to raise a to get back x, right? So what power do I need to raise a to get back x? The answer is y, okay? So that's what a logarithm asks. So let's look at some examples with some numbers. Maybe that'll help our understanding here. So maybe let's do like the log base 2 of 8. So here I'm leaving off the parentheses because it's just a number. It's clear that the logarithm base 2 is applying to 8. Log base 2 of 8, that's going to be equal to 3. Since if you take 2 and raise it to the 3 power, you get back 8. So just like with the definition of log here, we've got the base becomes the base of the exponent. The thing the log is applying to is the thing we're trying to get to. And the thing the log equals is that power. Okay, let's look at another example. If we did logarithm base 3 of 9, so we ask, what power do we need to raise 3 to get 9? I think the answer is 2. Since 3 squared, 3 to the 2, gives you back 9. Okay, we can do this for more complicated numbers as well. For example, we could do log base, like 25 of 5. So here we're asking, what power do you need to raise 25 to get back 5? I think the answer is going to be 1/2. Since 25 to the 1/2 is equal to square root 25, and that's just 5. Okay, so there's some basic logarithms. So moving between logarithms and exponents is an important skill. It's one of the skills that you're developing in the homework. So for example, if we started with some logarithm, let's say we said log base x, we can throw some variables in there. That's totally okay. Let's say it's applied to 1/2. Let's say it's going to equal 2. And we want to write this in exponent form. So if we write this in exponent form, we want to take base x, raise it to the 2 power, equals 1/2. Using the definition of logs from up here. Okay. So it's just figuring out where things go. Let me color coordinate so that you can really see what's going on. The base of the log becomes the base of the exponent. The thing equals is the power. And the thing inside the log is applying to becomes that right there. Okay, and then we can also move back the other way. We can go from exponential form to logarithm form. So let's say we had 9 to like some power y. Let's say that it was equal to like 37 or something. Okay, we want to write this in or not exponential, sorry. It's already in exponential form. We want to write this in logarithm form. So we do log base, the base of the exponent, which is 9, applied to the thing on the other side of the equal sign, so 37, and that's equal to the power, which is y. So again, you can see that the base of the exponent becomes the base of the logarithm. The thing on the other side of the equal sign here becomes what the log is applying to. And then the power on the exponent becomes that. All right. So now let's look at some basic log properties. So first, log base a, so a is any number here, of 1 is always equal to 0. And that's since any number raised to the 0 power is always going to be 1. We saw that in chapter 1. Second log property is that log base a of a is going to be 1. And that's since a raised to the 1 power, so any number raised to the 1 power is just, oops, not 1. You get back itself again. 3, the next two are very important. Log base a of a raised to the x power is x. So this, you can really see here that the log is undoing the exponentiation here. Log base a of a to the x, where a and x are whatever numbers, equals x again, right? And if we wanted to, write this in the same form as we've been doing, this is since a to the x equals a to the x, but that doesn't really give you any information. The main core idea here is that logs and exponentiation are inverse functions, right? They undo each other. And in fact, they can undo each other the other way, right? If we take a to the log base a of x, that's also going to equal x. So let me actually write that a new line a little bit bigger so you can really see what's going on. So a raised to the log base a of x is equal to x. Okay. So these two right here are key properties. And what they're really saying is that logs and exponents undo each other. So these will come back up in section 4.5 when we start talking about solving equations with logs and exponents. Okay. Let's talk about some special logs. So there are two special logs. The first one, log base e of x. This is called the natural logarithm. Right, just as e to the x is called the natural exponential function, or sometimes just called the exponential function. We talked about that in 4.2. A log base e is called the natural logarithm. It is usually written as ln of x. So usually I write ln so fast because I'm not going to lie, I use the natural logarithm a lot, all the time. So it's very important in mathematics in general. They usually write it ln. The other special log, just a little less useful, but still good to know, is log base 10 of x. And this is called the common logarithm. Oh my gosh, I can't spell. This one is usually written as just log of x. Although some, I want to say, computer scientists, they'll have log just log of x. They'll have that to mean the natural logarithm, and they won't use ln of x, which is horrifically confusing. But if you ever see just a log without a base, I mean log base 10, I mean the common logarithm. And that's usually what mathematicians mean. And if you see ln of x, that means the natural logarithm. Okay, before we wrap up this introduction to logs, let's talk about their graphs. So here's a note. Because the exponential function has a domain the whole real numbers and range from 0 to infinity, logarithms have domain 0 to infinity, not including 0. You cannot plug 0 into a log. And they have range whole real numbers, so negative infinity to infinity. So let's look at maybe a graph of one in particular. So let's look at the graph of, say, f of x equal log base 2 of x. Okay, let's make some points first here. Maybe do, and I kind of plan these out ahead of time because logs can be difficult to calculate by hand. I'm going to have x be a fourth, 1/2, and 1, 2, and 4. And notice I'm not going to try to plug in 0, nor am I trying to plug in a negative number because logs don't accept those. And so we want to know what log base 2 of 1/4 is. And if you do the math out, I think you'll find the answer should be -2. right? Because 2 raised to the negative 2 power is going to be a quarter. And then log base 2 of a half, similarly, is going to be negative 1. Log base 2 of 1, I think that was one of our log properties. That's going to be 0. Log base 2 of 2, another one of our log properties, that's just going to be 1. And then log base 2 of 4 is going to be 2, because 2 raised to the 2 power, so 2 squared is 4. Okay, so let's go ahead and plot these points. I almost feel like I don't have enough room, because this graph's going to be a little big. Okay, x-axis, y-axis. All right, so if we plot our points, let's see. At x equals a quarter, we have negative 2. So that's going to be about right here. And then at x equals 1/2, we have negative 1. Now here, actually, let me make these colorful so we can really see what's going on. So those points were here, here. And then x equals 1, we had 0. And at x equals 2, we had 1. At x equals 4, we had 2. So the graph of this function looks kind of like that. This is log base 2 of x. So an interesting thing to note here about this graph, reflect it across the y equals x line, we get back. Now, if we reflect our points, I think we get here and here, here, and then we also have here and right about here. And if we look at the graph of the reflected log, it's actually the graph of 2 to the x. Right, this kind of follows from section 2.8, where we talked about the graphs of inverse functions. Right, the graphs of an inverse function are reflected across the y equals x line. So now you can really see geometrically that logarithms and exponents are inverse functions. And so if you wanted a refresher on stuff like that, you can see section 2.8. All right. So those are some logarithms. We'll be working with them for the next couple sections. So I recommend you get comfy.